We begin our look at the adiabatic processes with this, a parcel of air. What is a parcel of air? Well, it's a bubble of air, and this bubble of air moves independently through the greater atmosphere, maintaining its own characteristics, primarily temperature and moisture conditions. If I was at the bottom of a swimming pool and I breathed out into the pool, my breath would exhale into the water, and then bubbles of air would float to the top of the pool and burst. The chlorine in the pool would not mix with my breath, and my breath would not mix with the chlorine, at least very minimally. This is kind of what I'm talking about. When I say a parcel of air, it's an independently moving bubble of air. Remember, the atmosphere is a fluid body, just like water is a fluid body. Neither of those things are a chair or a table. And within the greater atmosphere, it's possible for independent bubbles of air to move around. How big is a parcel of air? It could be as big as the college. It could be as big as half the United States. But just know that there are independent bubbles of air that will move around within the greater atmosphere. We call these things parcels of air. As a parcel of air rises, so it's going to move vertically in the atmosphere, it's going to go up into the atmosphere. It will expand and cool. And it's going to expand and cool because of decreasing atmospheric pressure combined with decreasing molecular collisions. So what happens is, as this bubble of air rises in the atmosphere, there's just simply less weight on it because it gets higher in the atmosphere and is above more and more of the atmospheric molecules that make up the atmosphere, thus less weight. That allows the parcel to expand. As it expands, the molecules within it have less contact with each other. When the molecules are contacting each other, this creates friction. Friction generates heat. Well, as the parcel rises, it expands, the molecules get further apart, and they run into each other less frequently, which generates less heat, and therefore it cools off. As the same parcel of air subsides, it will be compressed and it will warm. It's compressed because of increasing atmospheric pressure, in other words, increasing weight on this parcel. And it warms because of increasing molecular collisions. So you press the molecules together, they interact with each other more frequently. There's greater friction generates greater heat. Take a look at this diagram. So in the middle, don't worry about the 30 degrees, 20 degrees, and 10 degrees Celsius. In the middle, you have an independently moving bubble of air. It's not necessarily a cloud. This is just so that you can see it. And on the left-hand side, you see the blue arrow, and the blue arrow is pointing up, and it says expands and cools. So you can see what happens to the parcel of air. Down at the bottom, where it says 30 degrees Celsius, it's small, and then as it rises, it gets bigger and bigger. There's the same number of atmospheric molecules because it's the same parcel. The molecules just get further apart. And then you can see as the parcel of air descends, which is represented by the red arrow on the right-hand side, the parcel is compressed and it warms. So in other words, you can see that as it comes down, it's going to get smaller and smaller. Same number of molecules, it's just being compressed by the weight of the atmosphere. You probably remember this diagram on the left-hand side. This is showing you that as altitude increases, air pressure and air density decrease, then you can see 14.7 pounds per square inch, which is the weight of the atmosphere. Now look on the right-hand side. If the parcel of air we're talking about is where the yellow arrow is at, there's not a lot of molecules over the top of it. But if that parcel of air is down below that red line, you can see that there's significantly more molecules over the top of it, which adds weight. This is the reason that the parcel is able to expand and then contract. You've seen this before also. On the left-hand side, you can see the bag of chili cheese Fritos at sea level with the greatest amount of weight on it from the atmosphere, and then the same bag at 9,000 feet with significantly less weight from the atmosphere and less pressure on it, it's able to expand. This is what happens to a parcel of air. Same thing. When it comes down, it's compressed. When it rises, it expands. So the adiabatic processes describe what occurs to rising and subsiding parcels of air. But the air parcel must be moving vertically in order to apply the adiabatic processes. You remember before we had something called the normal lapse rate. Well, we're going to come back to that later, but the normal lapse rate is applied when air is not moving vertically. When the air moves vertically, there are other dynamics in play. And just to remind you, as a parcel of air rises, it will expand and cool because of decreasing atmospheric pressure combined with decreased molecular collisions. And as a parcel subsides, it will be compressed and it will warm because of increasing atmospheric pressure and increasing molecular collisions. Now we need to put the math on this. We calculate temperature changes in the vertically moving air parcels with one of two rates. The first rate is called the dry adiabatic rate, which is generally referred to as the DAR. It's not pronounced DAR, it's generally pronounced DAR. Dry gives away what's going to happen with it. The dry adiabatic rate is used under two circumstances. The first one is this: it's used every time the air is subsiding. So when the air is subsiding, there is nothing else happening. We always use the DAR. And when the air is rising and the relative humidity is less than 100%. How do we know the relative humidity is 100%? If there's not a cloud forming, the relative humidity is less than 100%. If there is a cloud forming, the relative humidity is 100%. So if the air is rising and there's no cloud forming, that means the relative humidity is less than 100%, and we will be using the DAR. The DAR is 5.5 degrees Fahrenheit per 1,000 feet. Notice we are doing this using the imperial system. The other rate is called the wet adiabatic rate, which also indicates when you're going to use it. The wet adiabatic rate is generally referred to as the WAR, not WAR, but the WAR. This is only used when the parcel is rising and the relative humidity is 100%. How do we know the relative humidity is 100%? Because there's a cloud forming. If there's a cloud forming, the relative humidity is 100%. No cloud, the relative humidity is less than 100%. And the WAR is 3.3 degrees Fahrenheit per 1,000 feet. There are four ways to induce air to rise. Orographic lifting, which happens when air rises up and over a mountain. Cyclonic lifting, which happens when air rises in a low pressure system. Convectional lifting, which happens as a result of surface heating, so the ground gets hot, especially during the day. The air in contact gets hot and hot air rises. And frontal lifting, which occurs when warm and cold air masses meet and the warm air is forced to rise. We will go through each one of these in more detail.